Hello engineers. Every structure we build, whether it's a towering scraper or a sprawling bridge or a pressure vessel, relies on one fundamental question. How much stress can this material safely handle? Welcome to the world of allowable stress values, the invisible limits that ensure our design don't just stand tall, but stand the test of time. But how are these values determined? What science, testing, and safety factors lies behind these numbers engineering trust every day? In this video, we will uncover the rigorous process behind establishing these allowable stress values, from material properties and failure theories to codes, standards, and real-world testing. Because when lives depend on your design, knowing the limit isn't just important. Before we dive into how allowable stress values are established, let's understand the three key mechanical properties that form the foundation of this concept. The first one is yield strength. So it is the stress at which material begins to deform plastically. Up to this point, the material will return to its original shape when the load is removed, and beyond this point, permanent deformation occurs. Let's take a simple example. It is a metal spring. As you stretch the spring, it resists the force and returns to its original shape. This is a elastic deformation. The material is still within its safe limits, but if you pull too hard, there is a there comes a point where the spring does not bounce back. It stays a stretch and permanently deformed. That's the yield point, and the corresponding stress is called the yield strength. Beyond this yield point, the material has entered the plastic zone and it's no longer safe for use in precise applications. And next one is tensile strength, guys. It is the maximum stress a material can withstand while being stretched or pulled before breaking. If you observe in a stress strain curve, it is the peak point. It is the peak point, guys. So let's take a simple example, that is the rod having force on both sides. So if you see here, the rod is under the tensile force. So up to yield point, the material will regain its original shape. After yield point, the material entered to plastic deformation. You will see here, this is the plastic deformation. After yield point to up to tensile, ultimate tensile point, your material in plastic deformation. There is no fracture, but it is in plastic deformation, guys. If you apply some more force after yield point, after this point, your material will turns to break. So this is all about yield and tensile strength, guys. I hope you understand. And next one is maximum allowable stress. So what is the maximum allowable stress, guys? It is the highest stress that a material can withstand without failing. It is the crucial factor in engineering design, especially for pressure vessels, pipelines, and structural components. The value depends on material properties and the operating conditions such as temperature and pressure. The maximum allowable stress values that are to be used in the thickness calculations are to be taken from the tables in section 2 part D subpart 1, guys. So for your reference, here I attached one material example. If you open ASME Section 2 Part D, you will find Table 1A, so which shows you maximum allowable stress values for ferrous materials. For example, if you take 13, that is 18 chromium, 8 nickel, SA24304 for material, it has a minimum tensile strength as 75 and a minimum yield strength as 30 KSI. And there you can also observe the maximum allowable stress values for different temperatures. So how ASME derived these values, guys? You are observing here values, right? So how ASME derived these values? So let's see. Basis for allowable stress values. ASME doesn't given these values randomly. So they are based on successful service experience and test data. This test data generally get from the ultimate tensile strength and impact testing. So from the testing, we will get this test data. So what is successful service experience means? If you take a SA24304 material, if a material has been used in the real world applications, if it is performed well in the known temperature and pressure conditions, so it is reliable as lab test data, guys. So we will use this SA24304 for your conditions which are it is performed well. Okay, and next one is if you take carbon steel, you can do tensile test, hardness test, and impact test generally. So based upon this impact properties or UTM properties, so we can choose whether this material is suitable for our application or not. I hope you understand. Based upon these two conditions, ASME given the formulas for finding the maximum allowable stress values. So let's see that. So the very first one is room temperature and below. So what does it mean? If your pressure vessel is operated between room temperature or below the room temperature, the ASME committee said that the maximum allowable stress shall be the lowest value obtained from the following conditions. The first one is minimum tensile strength at room temperature divided by 3.5. So this 3.5 is the factor of safety for your ASME Section 8 Division 1 code, guys. And next one condition is 2 by third of yield strength. So let's take with a example. So if you see here, I'm taking SA36 as an example, which has minimum tensile strength as 58 KSI and minimum yield strength as 36 KSI. So what is the maximum allowable stress for this SA36, guys, at room temperature? So these values are generally in room temperature. So we will find the room temperature, guys. So the first condition is minimum tensile strength by 3.5. So minimum tensile strength is 58 and divided by 3.5 will gives you 16.571 KSI. And next condition is 2 by third of yield strength. So our yield strength is 36 KSI. So if you find out, you will get 24 KSI, guys. So I already informed you, ASME committee said this maximum allowable stress is the lowest value obtained from this both condition. What is the lowest value you got from this both these conditions, guys? So it is the 16.6 KSI. So this is your maximum allowable stress value. I hope you understand this condition. So next one, ASME derived for above room temperatures. So what does it mean? At high temperatures, material can slowly deform or rupture over time. So allowable stress value is the lowest value of stress that causes 0.01 percentage of creep per thousand hours, and F average into stress that causes rupture in 1 lakh hours. This F average is the factor based on temperature and rupture data, guys. And there is one more condition, that is the 80% of minimum stress that causes rupture in 1 lakh hours. So if your vessel is operating at above room temperature, you need to satisfy, you need to take the lowest value from these conditions as a maximum allowable stress values. And next one is special cases. For some materials like austenitic stainless steels, nickel, copper, and cobalt alloy, two sets of stress values are given. One is normal values and another one is higher values. If you see here, I told you maximum allowable stress values for room temperature and below. So this one. For above room temperature, you have this is the normal value and this is the higher values. So where we use this higher value means, so in some applications, small deformations cannot impact on the application, guys. So in that cases, you can use up to 90% of your yield strength at the temperatures. So this is the table where you will get all the information related to maximum allowable stress values, so which is in ASME Section 2 Part D Mandatory Appendix 1, guys. I hope you got some valuable information from this video. So please subscribe my channel for more interesting videos, guys. Thank you.